Recording. Okay, so today we are going to do this something called complex assembly analysis. This is a CAD file of a VESA monitor mount. What is VESA? It's probably a standard lah for mounting all these monitors and TVs. So they have certain sizes lah. I think most common one is 100 by 100 lah. So meaning the screw size is 10 centimeter horizontal and 10 centimeter vertical. Okay, so this is the CAD file. So we need to download the whole folder. We're gonna see this one. 7-zip extract. So this is the CAD file of the whole monitor mount. So semua orang boleh download and open it up. So we are going to see full assembly lah of all the components. I think there are around 5 parts. Okay, so there you go. View, display. No, user interface. Task plane. Task plane kah? Yeah, task plane. I can turn off task plane. Okay, so this is probably done by one designer in Russia. I think this is Russian language. Okay, so let's inspect. How is this part being made? Again, it's in Russia. I don't know how to change the language. Probably you cannot do that because the inputted keyboard is already this one. So apparently it's done using sheet metal. Everything is done using sheet metal. And if you go to evaluate, you can measure the thickness from here to here. Ada tak? Measure this point to this point. Apa ni? Measure here to here. To here. Tak boleh nak klik ke? This one kot. The galong lah. Point to point, yeah, it's supposed to be here. This point to this point. Not really correct, 4 mm. So the thickness of this part is 4 mm. I suppose the whole part is being done using 4 mm thickness lah. If you want to change this one, is it possible? Maybe. I think you need to go here, edit feature. This one, the depth. You can change the thickness lah according to D1. This one. This is the band parameter. Edit component. Okay, so sheet metal, 4 mm thickness. What is the material? It's probably not stated here. Okay, so this is a monitor mount. I'm going to create, I think I have already. Finite element. This one. So semua orang dah checked. This is a VESA monitor mount. Okay, so let's check it out. Maybe take some photo and letak kat sini. So most likely we are going to get some loads center back, some loads mounted here lah. One force here, another one here, another one here, and finally here. So this is where you mount your monitor, and then all these things are going to be connected by pins, and this is load. So all the loads. Oops. Finally, the final load is here, and you're going to mount it here. Bolt point. So there are four places lah where you can mount your bolts. Okay, so let's decide on a material first. Monitor mount material. Most likely it's going to be steel, something rigid. I say, man, connecting plates are made of aluminum. Most likely it's steel. I can't find anything here. If something's very big and solid like this, most likely it's going to be aluminum lah. But if you are using sheet metal, most likely it's going to be sheet metal lah. Okay, so let's. I think this is it lah. This is the boundary condition and loading condition that we're going to apply. Quite simple lah. Okay, so let's do it. Let's go to your add-ins and click on simulation. And then go to new study. We're just going to use static for purposes of simplicity and faster. Use static. And we are going to number 1, apply material lah. So apply material to all. Let's search something that has some proper yield stress value. Carbon sheet steel, good enough. 1023 carbon sheet steel. 10 series. Steel material code meaning. Most likely you know about all this. SAE grade steels. So kita ada carbon steel. So benda alam macam ni kamu dah faham kan? I think you learn material science, and then you learn about engineering materials. So steel, kenapa jadi steel? Dia iron campur dengan carbon kan. So kalau kamu pilih grade 1 XXX is carbon lah. If you want to go things like stainless steel, most likely you're going to choose this one lah, chromium. Ini dah ada certain contoh. Carbon steel, nickel steel, nickel chromium, molybdenum, chromium vanadium. Ni stainless steel, chromium steel dia akan pakai stainless steel lah. Kamu kena ambil 5XX punya series. Major classification. So most likely this is important Tak tahu betul ke tak. Saya memang lupa lah benda ni. So we're gonna go for something cheap today. Kalau tadi stainless steel 5 kan, 5 punya series tak ada sini 4 je. 1023, 1020 pun okey. 1020 steel cold rolled, iron base super alloy. Kalau kamu perasan kan, whatever material that you choose, the elastic modulus is almost the same. 2 point, ini 2 GPa lah. No, 200 GPa, right? G is giga 10 to the power of 9 kan. So 200 GPa. Ini pun lebih kurang sama, 200 GPa. Ini ya 200 GPa. Whatever steel you choose, elastic modulus is almost the same. Benda yang berubah adalah this one je, tensile strength and also yield strength. These are the things that changed according to the additive lah that you put lah. Okay, so we're gonna just go simple this one. 1023 carbon sheet steel. So okay, this is the material that we choose. Besar lah pula. Okay, there you go. So you can apply lah. Apply this to all. So take note, the yield stress is about 282 megapascal. No. So yield stress equals 282 megapascal. Elastic modulus itulah 200 GPa, sama aja. Elastic modulus uh, 200 GPa. Besar sangat ah. Other things is poison ratio 0.29. Benda yang penting kena ada kan. These are the things lah yang penting. Boleh kah? Hampa tengah buat kah? Okay. So the thing that we need to do is we need to apply things like material done, fixture, right click, fix geometry. You can apply to here for X, 4 locations, here, and also here. So we have done fixed geometry there. Next, we need to do some loads lah. External load. So most likely it's going to be force. So we are going to apply at all the screw points here, here. Ini kat bawah lah, yang bawah ni dan yang bawah ni . So all 4 points. So next we need to choose a selected direction. The direction would be something vertical like this. What is the force value here? Reverse direction. So maybe about maybe let's test 20 kilo first. TV berat tak berat sangat aku no. 20 kali 9.81. So 196.2. So one is the important thing that you need to do is that you need to change this one lah from per item to total. So if you change per item, you're going to get berapa kilo tadi ya? 20 kilo kan? 20 kali 4 lah, 80 kilo. So this is wrong. So make sure you choose total. Okay. Something to take note. So let me make it a note inside here. New slide. Let's make it a note. So make sure You choose total, not per item. So it has to be total load, not per item. Okay, so you can easily forget this thing. So that's why you have to check your work before you submit. Okay, so this is done. It's going down. So click on OK. Ha. Oh, direction ada angle tu Okay, so kalau direction ada angle, paling senang adalah kamu kena pergi sini. Reference geometry, tekan plane. So kamu nak buat satu plane lah kan. So plane ni mungkin kamu nak buat angle. So choose something vertical. Contohnya sini. Dia jadi plane flat macam tu kan. Kamu pilih satu lagi. Oh, dia jadi angle macam tu. Angle ni pula kamu boleh ubah lah. What is the angle? Boleh lah ubah sini. Current combination or reference are not valid. Oh, sebab saya pilih dwarf plane, dia terus jadi 45 degree sebab saya pilih plane ini saja, saya bolehlah letak angle. Boleh lah ni 45. Dia jadi macam gitu Dia tak betul Okay, jap. Tekan reference geometry, tekan plane. Kamu pilih satu plane, lepas tu pilih satu line macam tu. Dia bolehlah pakai angle 45. Kamu kena play around sikit lah. Macam tu. Dia memang intelligent lah. Pilih plane dan pilih satu edge. Dia anggap ini adalah satu angle. Ulangan. Reference geometry, plane. Kalau kamu pilih dua surface, one surface and another surface, dia automatic jadi 45. Meaning dia ambil intersection lah of the two planes. Satu cara. Satu cara lain adalah reference geometry, pilih plane, pilih satu surface dan pilih satu hujung ni, edge. Kalau jadi macam tu, kamu boleh ubah angle ni jadi 45. So, kalau jadi 45 macam tu, okay. So, adalah, for example, saya nak apply load If I go to here, another load, force. Saya pilih dekat sini. Tapi saya pilih selected direction, plane 1. Boleh ke? Plane 1, lepas tu saya pilih normal to the plane. Reverse direction. Macam tu. Dia jadi angled like so, following the plane direction lah. So this is the way to control lah, to control your force direction. Ini menggunakan reference geometry. Cara kedua, delete. Cara kedua adalah apply load, apply force dekat sini kan. Selected direction. Katalah saya pilih dia minta reference plane kan. Katalah reference plane kamu pilih apa-apalah Katalah ini front plane kan. Kamu boleh apply dua force lah. Satu force, bukan ini yang ni. Ke atas katalah saya pilih 10. Arah sini pula 10. So dia jadi dua benda lah. Kalau lah hampa nampak So kalau benda yang dua benda ni, kamu boleh pakai macam resultant lah. Ingat lagi apa macam tu Draw force Kalau kamu ada satu force macam tu and another force like this, dia akan ada resultant macam tu kan. Katalah ini 100 Newton, ini 45 degrees. So ini akan jadi 100 cos 45. Ini akan jadi 100 sin 45. Bolehlah juga buat macam ni. Apply two forces, one vertical, one horizontal. Kamu akan dapat ni lah, F resultant. Tapi cara ni crude sikit lah, kena kira berapa resultant dia. Cara paling mudah lah macam tadi lah, kamu buat reference plane. So once you have the reference plane, you can apply in whatever direction you want lah. There you go, habis cerita. Right click, delete. Reference plane ni, if I wanna delete, also can lah. So forces done, boundary condition or the fixed geometry done. Next is we need to look at component contacts. This one. Kalau tengok saya punya ni kan, Control 8. Dia akan apply lah all the time global contact for something touching. But if something is not touching, for example like this, it has a gap. So if it has a gap, this thing is not valid at all. If it is touching, then it is valid. So one way to check it, you can go to evaluate and click this one, interference detection and calculate. So ini tak ada apa-apa yang touching lah. Satu benda lagi kamu boleh pilih ni kan, treat coincidence as interference. Click this one and calculate also. There is, ada, oh ada ni, one thing which is touching lah, this one. So ini je lah yang akan touching. Ini saja yang akan digluekan lah. Sebaik saya check. Which is not correct lah. Ini. Tengok dari atas. So if I apply this global bonding contact ni kan, so ini saja yang akan, ini dia akan glue lah. So dia tak akan detect as pin joint. So global contact ni most of the time kamu kena delete lah, unless kamu betul-betul very sure you can use this global contact, you can proceed lah. Tapi most of the time kamu kena delete. Right click, delete them, because most of the time it's going to make your model wrong. Sebab dia welding segala komponen. So delete. So once delete, kamu kena apply sendiri connection sendiri. So whether it's going to be contact or component contact. Kalau nak apply balik sekali yang benda-benda kamu delete kan, go here lah, component contact, tekan bonded, tekan global. Dia akan join balik lah segala-galanya. This is the way to do it lah if you want to apply global contact, but we don't want to do that lah. It's okay. So we have all these pins, so we need to apply something called pin connection. So go here, baru setengah jam right click, click on pin, choose pin. Okay, so choose lah two surface, one here, the other one is at the bottom, and then there's two things lah, which is one is with retaining ring, meaning dia boleh putar lah, dia boleh putar kiri dan kanan. Satu lagi kamu lock dia, so you can do it freely moving ataupun kamu nak lock dia lah. So in this case, kalau kita nak bagi model kita stable, kita kena lock lah. Kalau kamu tak lock dia, model kamu akan bergerak lah. Bergerak how? Katalah saya maintain macam ni, with retaining ring. Sekali lagi saya apply load kan, dia akan bergerak-gerak macam ni lah. So bila bergerak-gerak macam ni, dia bukan lagi static lah, dia akan jadi dynamic. So most of the time kamu kena bagi dia lock. Sebab bila model bergerak macam ni kan, dia bergerak freely like this, your model is no longer static lah. So if you're doing a static analysis, everything should be rigid lah. So you have to change lah this pin connector, edit definition, choose this one. No motion So print screen. This is probably something important for you to remember. Ini saya boleh delete ko lah. Delete, Ctrl paste. Okay. Make sure it is with key, meaning there's no rotation. So you have to repeat lah the same thing. Ada 1, 2, 3, 2, 4, 6 and 8 lah. 8 tempat lagi lah kamu kena buat pin ni. Pin ni boleh ke copy? Tak boleh Boleh no, copy. Boleh lah. Kau nak cepat copy. Tak boleh lah. You have to do it all the time. Right click. So quickly do it. Pin this surface and pilih yang pink pula. Here. Make sure you no rotation. And then another one, pin surface here and surface bottom, no rotation. Pin lagi. I should probably keep quiet. I cannot stop talking. With key, no rotation. So the pin will be created for you lah. You no need to draw your own pin. Here and also at the bottom, no rotation. I'm down to my last 3 pins. Here and at the bottom. Here, no rotation. And finally here. Pin somewhere here. Click. The next one will be here. No key with key, no rotation. And last one dekat sini. Pin over here and over here. So that is done. So dia jadi rigid lah. Dia tak akan bergerak-gerak macam ni lagi lah. Dalam FEA lah tak gerak-gerak. Kalau dalam model kamu memanglah dia bergerak lagi Dia masih bergerak lagi. But inside FEA dia tak bergerak dah lah once we export to FEA. So kalau kamu nak make sure kamu punya model ni straight kan, straight line, kamu kena play around dengan mate lah. Ini initial condition ni kan, kamu kena play around dengan mate. For example, you can go to model. Kamu kena tekan kat mana? Assembly, tekan mate. Parallelkan dia lah. This surface to this surface. Cannot be moved to this parallel. Maybe perpendicular, mate. Perpendicular. This one to this one. Okay, boleh. And perpendicular. Bukan perpendicular this surface to this surface. Okay, done. And then lagi parallel this surface to this surface. Okay, straight line. Sekarang once kamu apply mate, dia akan jadi rigid lah. If you go back to your motion to your FEA, dia tak boleh lah gerak-gerak lagi. like it used to be. It's going to be straight like this. Why do we do this? Because when your monitor is in open mode, the longest to your original fixture, this one will be the highest condition lah. Dia akan ada moment kan. Kalau dia rigid macam tadi kan, macam mana? I gotta go back here and disable this first. Right click. Kalau saya suppress, dia bolehlah gerak-gerak balik. But you don't want to run your analysis in this mode. Why? In this mode, the load is not so severe, right? If you apply load in this condition, it's not severe enough. You need to apply it in the worst possible condition. So treat it in the worst possible condition lah, which is when all these things are open. Right click, unsuppress. Oh, they failed through here. Let me suppress it first. Dia tak boleh nak resolve lah. Kamu buka dia sikit, bagi dia okay sikit, and then unsuppress one by one. Unsuppress one by one. Unsuppress all the thing together, dia akan fail. Okay, so it's like this. If you go back to your static analysis, all the pins are there, the loads are there. So we are done with boundary condition. It should be looking like this. New slide. So it's looking like this lah, with all those pin joints. Next is we should do something called meshing. Currently everything is in sheet metal lah. Kalau kamu mesh sekarang, right click. If you create mesh, everything will be mesh using sheet metal lah. So you can run like this also, tapi kamu kena make sure kamu punya boundary condition tu betul lah. You can run like this because currently this one is center, right? The boundary condition. Bolehkah kita run macam ni? Let's try. If you get error, you can just convert to solid lah. Maybe you want to save first. File, save all before you do anything. Maybe I should check for mesh plot aspect ratio. The maximum is 12.4. That's good enough. So mesh quality, this is the one. So you can run lah. So click on run this. So this is run using what do we call, shell elements. So everything is run properly lah, and you get whatever. You don't get any failure yet lah, because yield stress is about 282. You are below 200. You are about 270. Where is the location? Edit definition go. Where you can show the maximum. Show maximum annotation. Click on OK. Highest one is about here lah. Ini. So part ni je lah yang problem. Part lain-lain tu tak ada masalah kot. So you can also show this thing in plot tools, ISO clipping, bukan, mesh sectioning. Tarik dia kan, tarik dia section ni. Kita nak tunjuk dia punya mesh edge. And also you want to turn off this section plane. So kalau macam ni, kamu boleh publish kamu punya result dalam keadaan ada mesh lah. So this is how it looks like. Okay, everything has been run using shell condition, and we only see problem like this. Of course, if you want to go more detail, you can create a better mesh, make it finer a bit, and then you can run it again. This is a finer mesh. We have a slightly problem here. If you wanna increase mesh size here, you can do that. Right click, apply mesh control. So maybe this area you want to apply mesh control. Tapi benda yang kita apply ni adalah dalam keadaan 3D. For example, you want to apply mesh control here, and also here, and also at the top, Currently the size is about 2.2, so maybe kamu nak buat maybe dia lebih kurang 1. So area tu dia akan kalau kamu run mesh sekali kan. So let's check it out. Currently it's like this. Print screen. Let me look at it. And then if you run mesh only, right click, create mesh. What happens when you apply some mesh control that area? Dah lama ni, 45 minutes. We're gonna finish at 1 hour only lah hari ni. What does it look like now? Does it get slightly better? Roughly like this. Lebih kurang je. Ada sikit kot. Perbezaan. Sedikit sangat ke? Seems like sedikit sangat lah. Maybe you can tukar mesh control kamu tu. Edit definition 0.5 mm. Run it again. Critical areas are where you want to refine your mesh. Print screen. So a better mesh control. From 1 mm, I think, tak ingat lah. Can't remember already. Mesh control. Control C, Control V. Mesh size lah equals 0.5 mm. If you're doing critical work, maybe you wanna change this one lah. Ini 1.0 kot. Ini dia tak ingat Entah 1.5 kot. So you can refine your mesh to get more accurate result at critical area, okay? So critical area. So if you're done with that, maybe you want to run it again. Did we get roughly the same results? 362 kan dah naik dah. Tapi tak boleh percaya sangat lah. Sebab ini adalah area where you have stress, concentration, and singularity effect is going to affect also. Kalau kamu kecil lagi, dia akan naik sampai bila-bila pun. So this is something that you need to take care lah. How to do that? Number one, kamu boleh buat linear static analysis. Bukan, non-linear analysis. Bila dia yield dia, you just treat that area as yield lah. One way to do it is just double click here. Maybe you want to see yield strength 282 kan. 282. So anything greater than that, just treat it as greater than yield. So you want to avoid all that lah. Paling safe adalah design everything below yield stress. So this is one way to do it. So you might want to take a look back lah at your design at these critical areas. The rest of the parts doesn't seems to have any problem. Kamu boleh plot juga something called displacement. Show displacement. Tengok macam mana? Tengok from the side. Alamak, ini saya kena tukar kot. Ini tekan maximum, minimum balik Reset. Oh, memang maximum dia 1 just nicely. Where is it? Edit definition. Chart option, show maximum Maximum dia kat sini lah. Sini. So roughly monitor ni kalau kamu mount dia 20 kilo, dia akan turun bawah lah by 1 mm. Where should I paste this result? Somewhere here. Ini duduk atas lah This is the first model. Okay, so that's one way to do it. Another thing that we encounter in class is that sometimes when you do some modification using your shell, it can fail. So something like this happens. You can always convert all this to solid lah. Right click. Treat selected bodies as solid. You can also do this. Sometimes it's more accurate also. So kalau kamu run mesh sekali lagi, create mesh. By right dia akan mesh balik jadi solid lah. Print screen. Kat mana saya tukar tadi, saya lupa nak tunjuk Tak ada lah New slide. How do I do this? Saya kena tukar balik shell. Tukar balik as mana dia ni? Define shell. Sudah hilang lah Define shell by selected faces je yang ada. Can I undo? Can Ctrl Z? Tak boleh lah. Okay, never mind. So something like this you need to run again lah. So shell bagus kalau benda dia tu very big and very thin. But if something solid like this, you might want to consider solid lah. Benda-benda yang kecil macam ni kan. Maybe 4mm is already very thick. And in order to get accuracy, you need to treat it as solid. So maybe it's a good idea lah to change to solid also. So click on run. I think there's a ratio, right, between thickness and the length. If it exceeds certain things, treat it as solid. Ini saya kena tukar balik Tukar balik, change to automatic. See, dia dah kurang jadi 245 something saja. So kalau kita model as shell, dia akan jadi excessively high Mungkin kamu pening kan, kenapa nak pakai shell ke, nak pakai solid ke apa kan. Memang macam ni lah. Most of the time kamu akan buat comparison between design A and design B. So kalau kamu apply the same boundary condition and the same meshing condition, kamu memang boleh buat very good comparison between design A and design B. Value dia lari sikit lah, kadang-kadang naik, kadang-kadang turun kan. But if you do a comparison between both design, you can get very good correlation lah. Ini bila saya tukar jadi solid, dia dah lari maximum sini 245 saja. So there will be changes lah. This is about 245 stress. And let's check out displacement. Sama tak Displacement show. Tapi displacement dia okay It's quite consistent. Something reliable is displacement lah. Stress ni memang not so reliable. So you have to be very good lah with results interpretation in order to read things like stress results. Okay, so 1 mm roughly is about 1 mm. Roughly stress value is about berapa tadi show, it's about there lah. 20 kilo kan kita letak kan. Apa lagi benda boleh cari So this thing is problematic. Kalau kamu nak tengok ini saja, boleh tutup yang lain lah. Right click, tekan kat mana there's no hide here. Maybe you can hide from here. Right click, hide. Boleh lah. Di sini, sini pun hilang lah. Can I show the result again? Stress. Boleh lah kalau kamu nak pening nak tutup yang lain kan. You can turn off other things in order to look at this. So of course lah, you can take a look at design and change certain areas here, reinforce, maybe make it thicker, change how we are going to support this, change your bending in order to improve this one lah. Maybe make it flange or some sort. Okay, so banyak kamu punya komponen kan, berlambat komponen kamu. I think it's about 6 kot. 1, 2, 3, 4, 5 components only. But the main thing is only this one, right? Main thing benda Allah ni je yang problem. If you look at stress value. So kalau kamu nak smart lagi kan, kamu boleh model benda Allah ni saja yang dalam analisis kamu lah. If you want to do that, what can you do? You can go here. Or you can go here. Go to the model. You only want to model this one. Right click this one. Click on open. Also can. Okay, another 5 minutes and we're done. So this is the only part that you want to take a look. For example, so in order to analyze this part only, you can go to simulation, click on new study. Don't worry, it's going to take about 5 minutes. Kita dah apply material kan. Treat as solid. Right click, apply, edit material. Tak betul ini change back to our material just now. Steel 1023 kan. Apply. Apply this material. So there's no more connection lah kalau kamu run satu analysis saja. Just go to fixture, fix geometry. Look at this part, this part, this part, and also this part. Apply. Ini kita nak apply load saja. Berapa load nak apply? Macam mana? If you go back to this one, right? The load is like this. Kita ada bolt, lepas tu load dia duduk jauh kan. So something like this. Kamu tak boleh lah apply load tu terus kat situ kan. If you apply that there, you will lose all the moment. So you need to really take a look at the moment lah. So maybe you want to inspect first. Models rebuild. Tak payahlah. Kamu measure dulu Evaluate. This measure distance daripada center hole ni kepada mana? Sini lebih kurang 216 mm kan? Perasan tak tu? Print screen. Create another one new slide. So jarak dia lebih kurang 216.67 mm ingat So something like this kamu tak boleh apply If you model only one part, kamu kena guna something called this one. External load ni, kamu tak boleh pakai force lagi. Kalau pakai force, dia akan lose moment lah. Kalau apply force boleh. Apply kat sini kan. Sini betul tak? Pin kan? Pin. Tapi dia hilang lah moment tu. Dia jadi shear force sahaja. So you don't want to do that lah. Dia akan ada error sikit lah. Tak apa, kita nak tengok perbezaan dia kan. Force. Kita nak tengok perbezaan dia. Sini satu force. Sini satu force. Selected direction. Vertical. Macam tu. Lepas tu kita tekan apa? Reverse direction. 20 kali 9.81. Dia ada total Make sure total. Kalau kamu buat macam ni, lepas tu kamu run terus kan. Create mesh. And then you run only. Dia tak berapa nak betul ya. Sebab you lose the moment. Kita punya stress value jadi around 62 something saja Print screen. Ini kamu apply direct force. So kamu dah underestimate lah ni. Underestimate. What is this? This is direct force apply. Direct force apply. Equivalent to not accurate. Loss of moment due to length length of 217 mm. So this is not accurate lah. Tak boleh apply force saja, kamu apply moment satu lagi. So kena apply dua benda lah. Force and then you need to apply torque. So you can do that. Or you can ini tak payah saya buat lah. Kamu boleh apply juga torque sekali lagi Ataupun kamu tukar macam ni. Right click, delete. Yes, delete. Kamu apply something called remote load. So remote load, kita nak apply dekat sini dan sini. Tapi location dia, kita punya distance kan, paksi Z This is Z, so it should be Z lah. 217 mm. Boleh lah. Berapa load dia? Load dia in Y direction kan. So Y direction 20 kali 9.81. So do like this. It's applying something called a remote load. This is much better and more accurate. This is what you should be doing. So ini nama dia. Something called a remote load. Accurate. Ni tulis apa? Moment due to length 200 cm is considered. So this is what you should be doing lah. And then let's go here and then blah blah blah. It should be okay lah. Click OK. And then you need to run it again. Tu dia. But don't worry about this. Ini dah deformation scale 100 kali ganda kan. Kalau kamu tukar deformation scale, true scale tak nampak pun lah. Tak nampak pun. Tu dia Ini lagi tinggi lah dia punya stress value dia. 422. Where? There you go lah. But of course don't be too alarmed. Kamu just compare design A, design B. Stress value might vary very much. But if you are comparing design A to design B, it should be fine. Ini adalah result to due to remote load. So if you don't apply the moment, it is not accurate lah. It is underestimate. Okay. So that's it for today. Okay, so you learn about applying components and applying remote loads, changing to solids, and such. Okay, so is there any question? Sampai component bulk. Okay, so okay, so kalau nak mudah kamu just fix kan. Kalau nak mudah, what I've been doing, I just fix this one lah. Fix pakai fix geometry. So dia lebih kurang macam bolted lah. Kalau kamu nak pakai bolt betul-betul kan, memang kena buat macam tu lah. If you want to apply a proper bolt, you cannot use this fixed geometry anymore lah. Right click, delete this fixed geometry. Kamu kena apply connection, kena apply ni bolt. So bila apply bolt, dia kena ada satu wall. So memang kena buat satu wall lah. Macam mana nak buat wall tu? Kalau kamu apply bolt kan, dia akan minta circular edge of the bolt. I think this one kot. This one. Ni, hujung ni saja. Lepas tu sini. Tak boleh dia kena buat satu-satu rasa. Circular edge of the nut hole. Circular edge of the bolt health. Bukan. Ini untuk dua komponen. Sebab tu dia ada dua benda Kalau kamu apply connection bolt, dia kan ada dua komponen lah. Kamu nak clamp dua benda. So dia minta 1 dan 2 lah. Depan dan belakang. Something like this, you need 2 komponen lah. Kiri dan kanan kan. Kalau nak apply dekat dinding, it's called I think it's called fixture. Fixture tapi ni foundation bolt. Ini untuk apply ke dinding. Apply dinding, use foundation bolt. If you want to join 2 components together, you have to use connection bolt. So if you want to apply to the dinding, you have to use foundation bolt. Foundation bolt dia akan minta lubang, this one, dan satu surface. Surface ni kena buat satu surface lah. Kat mana nak buat, memang kena create reference geometry plane, pilih belakang ni lah. Plane 1 tu. Plane 1 tu will be your wall, which is foundation bolt. This one, plane 1. Dia join tu lah. Diameter dia, ini dia automatically pilih kan. Nak pilih tight fit pun boleh. And then this material lah, tensile strength semua ni. Kalau kamu tekan OK, dia akan betul-betul create bolt kat kamu lah. Result ni saya hide dulu dia betul-betul create foundation bolt to the wall yang tak boleh bergerak. Something like this, kalau kamu run, blah blah blah, run. Rigid virtual wall contact must be defined for the foundation bolt. Dia kena buat contact pula. Connection, contact set, no penetration. This wall dan this wall kah? Bukan. I think contact set ke component contact tak tahu. Ni no penetration ni, I think. 2 or more bodies. This one, 2. I think there's I think I've shown this one. It's kind of 3D solid yang first punya lab tu kot. Saya rasa ada. Let's check out. This one. This one. Virtual wall. This one. Contact sets. Kena pilih. Virtual wall. Where should I go? Contact set. Pilih. Virtual wall. Faces and target plane. This is the face. Belakang ni. Target plane is this one. Macam tu. Barulah boleh. If I run it again, saya akan run dia dengan satu bolt lah. Preload. Okay, tak ada preload ni. This is a more complicated way to do it lah. Kalau kamu tak ada concern sangat dengan bolt ni, tak perlu pun. Unless kamu ada concern dengan bolt, yeah, you can do that lah. It's taking along. Oh, ini tak perlu sebenarnya. Kalau saya pun saya tak buat foundation bolt ni. Saya just fix geometry saja. Fix geometry ni is good enough. 2 3 4. Most likely kamu punya bolt tak fail pun. You can over design your bolt lah. Kamu just pakai fix geometry. The moment kamu run, just go here. Right click. List result force. Reaction force. Okay, cari kat sini. 1 2 3 4. And then update. Ini je lah. Inilah jawapan dia. Saya buat macam ni je selalu. Tak payah buat foundation bolt tu. So, in this case, kamu akan nampak Pak CY kan? Pak CY tinggi lah. Negative 49. Pak CZ pun ada, no? So, dia duduk moment kan? Dia duduk moment, dia nak tahan benda tu lah. Wah, ini very good lah. Pak CZ is very high. Inilah jawapan soalan test hari tu. Kamu just list result force. Kau boleh tengok kita punya axis Y kan. Y dia tahan total 20 kg kali 9.81 lah. Tapi Pak Z dia kena support axial pull due to something is trying to pull it out lah. It's about 300 Newton. Ini lebih mudah lagi lah untuk kamu cari bolt punya reaction force. Just pakai macam ni ya. Okay, so anything else you want to ask? Siapa ada soalan lagi? Before we end the session. Going once, going twice. Okay, so that's all for today. Thank you very much for coming. Ada ramai je. So later on I'm going to open up the attendance sekejap. So I'm going to turn off my recordings. Stop.